placed on our YouTube channel. So we are starting the recording now. I hear from someone that the audio is not very good. Could anyone else who's having trouble please note it? There's nothing I can do on our end. I'm using a microphone right now, so I hope things clear up for everyone here. Okay, getting some feedback on good audio. Okay, again, so the topic of discussion today is what is CO AirFree, carbon monoxide air-free, and I'm President and CEO, Bill Spohn, President and CEO of TruTech Tools. We're going to cover what this topic is. TruTech Tools, we do carry a lot of different test and measurement products and accessories. And we want to see you do it right, basically. That's what we want to do. There's a lot of different ways you can connect with us, and we'll be going over those towards the end of the session today. Again, the session is being recorded, so it will be placed on our YouTube channel shortly. With regard to BPI CEUs, and this is only true for people that are actually attending this class live and through unique individual login, you can actually get up to 1 BPI CEU for this class. Best thing to do is to stay on the screen, don't drift away. The webinar system can actually keep track of attendance or attentiveness. And right now I'm seeing most of the people that are watching are staying on the screen, so that's a good thing. Don't click on other screens or you may get dinged on your credit, and that's totally up to BPI and how they evaluate the credit from the session. Biggest question we get, besides technical ones, is a question like, when do I get my CEUs? TruTech submits the report from the system to BPI in 72 hours. After that point, it's in BPI's hands to evaluate and to assign and to give credit on your certificate account with regard to CEUs. So pretty much it's out of our hands faster than you could probably contact us. So we usually have things all squared away in our end. Your next stop on that, if you don't have your CEUs, is to check with BPI. And you can either do it through this email address or the phone number is given on the screen. And again, simply watching the recording will not allow you to get CEUs. So if you're watching it afterwards, this is mainly for your enlightenment and edification, as they say, but is not eligible for CEUs. Only the live classes are. We will be running this session again. Look on our webinars page, trutechtools.com/webinars, to see our webinar calendar, and we will be rescheduling this as a live session. There'll be more live sessions coming up. So why are we even talking about CO AirFree with kind of renewed intensity like we never have before? Well, CO AirFree is now a part of the BPI 1200 standard, which is a standard practice for basic analysis of buildings. It's going to replace some of the things you're already using with BPI standards that are now in existence. Excuse me. The thing to keep in mind is it's still in draft. So there are things that can change with it. It already has been through one round of comments, and I believe it'll be issued for another round of comments sometime later this summer, probably within a couple of months. That's the read that I get from BPI. It is an ANSI standard, which means it's part of the American National Standards Institute. That means that it's a standard that's constructed with a lot of different input from a lot of different parts of industry, of the industry that we're working in. The public review period initially was closed on November 18th, 2013, and another one is scheduled, as I mentioned before. The standard is not yet put into practice, but from what I've heard from different trainers, they're given the notion that they really should be looking towards training to Section 7. And Section 7 is the technical part of the standard, the test and measurement, the diagnostic part of the standard. And we actually have another webinar that we've run, and we'll run again live, and we'll also have a recording available where we talk about all the different changes to your test equipment that kind of roll forward as the changes in Section 7 have come about. The download's not available now on the BPI website. That's because there's another standard called Standard 1100, which is not the technical standard, but it has also to do with housing testing. That is currently out for comment now. They didn't want to have a confusion between having two standards on the website. So I will send everyone who's attended this session a link to a previous copy from September 2013 of the BPI 1200 standard so you can take a peek at it. And again, remember, it's not in practice at this point. So here's a copy of the index from the standard itself. What I've highlighted here is the combustion appliance and fuel distribution inspection, which is really where the meat of the matter is in terms of testing. So we're going to, that's the part that we're going to dig into some subsections here. If you're not familiar with ANSI or national standards, really these kind of really strict technical standards, if you see the word shall in the standard, it indicates a mandatory requirement, which means it translates to you must do. You must follow that standard, that part of the standard. If you see the word may in the standard, that indicates a permission. You're allowed to do it. It's neither a requirement or a recommendation, but it's okay to do. So you really have to pay close attention, and we will as we go through this thing and talk about what shall be done, what really needs to be done. Should or is recommended means it's not mandatory, but it's just a good idea. It's good practice to follow that part of the standard. So shall, may, should, or is recommended, all different meanings, kind of nuanced here. You want to take a look closely at that as you read the standard. The subset of the standard we'll be looking at now is that has to do with carbon monoxide measuring equipment. And of course, carbon monoxide is CO, carbon monoxide, one carbon, one oxygen molecule. That's the toxic gas that is a cumulative poison that has really severe health effects on people and animals. And we actually cover this more in depth and more in detail in our combustion analysis webinar. And I'll take you to our webinar page before we leave here today, if in case you want to sign up for more webinars or just see where the page is, and we go into these kind of topics in a little bit more detail. Okay, I'm being told by someone that the standard 1200 is actually in practice. I'm not sure that's true. I would have to check with my resources at BPI. I'm not sure that's true. But it is, I do agree with it. The final comment is a strange transition period to be working in. Okay, let's move on to the next section here. I'll make sure I keep my window open. So in section 7.2.4.1, they talk about the range of the carbon monoxide meter, and it must be a meter that displays in levels of up to 2,000 parts per million. Pretty easy task, pretty straightforward, something that can be done in terms of the most of the analysis equipment that you have at hand right now. In 7.2.4.2, carbon monoxide air free is discussed. And now what we're looking for, what the standard is looking for, is an instrument that's capable of measuring, displaying air-free CO concentrations up to a certain level. As I've gone through the standard, indicated that these are actually words pulled from the standard. There may have been a typo in there because it talks about air with a high level of oxygen concentration, of which doesn't make sense. So we're going to be talking about CO AirFree calculation from my interpretation up to about 10,000 parts per million is usually what you're looking for from the analyzer or meter. CO AirFree is also called CO undiluted, or on some meters CO UNDIL for undiluted. These really are equivalent terms that mean the same thing. Really what we're talking about is removing the impact of the diluting air from the calculation, from the measurement. So that's really what's happening here. Now let's take a look at a combustion diagram and take a look at see where does CO AirFree come from in kind of a conceptual standpoint. So we have at the bottom here what's sometimes called the combustion triangle, with the three things that are required to have combustion take place, and that would be fuel, oxygen, and a source of heat. So the fuel is hydrocarbons in the fuel, oxygen is present, and then a source of heat or source of ignition cause a chemical reaction and rapid oxidation, which then generates even more heat, which is usually the goal of combustion. And then it also results in a chemical change of the elements that go into it. So the carbon and the oxygen form together to make CO2, and this would be in perfect or complete combustion, and the hydrogen and oxygen form together to make water vapor. That's pretty much it. That would be perfectly balanced, perfectly complete combustion. I'm going to take a real quick look at my questions here. Uh, so here's the three elements that go into it, and pretty much the three things that you get out of combustion. So you have the three: oxygen, fuel, and the source of heat or ignition. You get more heat, CO2, and water vapor out. Now, because we made a little change here, we turned to incomplete combustion. And incomplete combustion is when combustion doesn't go totally to completion. You end up with things like carbon monoxide. If there's not enough oxygen available for the fuel as it's trying to oxidize in the combustion system, you can get the creation of carbon monoxide, which doesn't make it all the way to complete CO2, but makes it the CO. That's the toxic gas that we're really concerned with here. The other thing we've added here is the fact that air is the source of oxygen, and air is mainly made up of oxygen and nitrogen, and actually about 20.9% oxygen and about 78% nitrogen. And the rest, there's some other stuff in the air, which is really as important to our argument today, but mostly it's nitrogen and oxygen are in the air. In incomplete combustion, in traditional or actual combustion in the real world, you have excess amounts of air going through the system, and coming through is an excess air measurement on the outside of the system. And that's usually detected or estimated by looking at the actual oxygen concentration that's coming out in the flue gas. That would tell you how much excess air is present. The stuff in the air, and as well as nitrogen and sometimes other chemical compounds like sulfides and things like that, can produce toxics, which would be nitric oxide or sulfur dioxide or acidic type vapors. Now let's throw in here the stack. This is where the flue gas is moving through, and the probe from your combustion analyzer, and take a look at what this is what the combustion analyzer is actually measuring. It measures the thermocouple measures the heat, the carbon monoxide sensor measures the carbon monoxide, the oxygen sensor measures the oxygen. CO2 is actually calculated from some well-known properties of the fuel and the amount of excess air. Water vapor usually isn't measured, and sometimes the toxics are measured. Now we'll make a little change here and throw this box around the carbon monoxide and the excess air, and look at those two things together. And if we could look at them together and somehow remove the effect of the excess air, these two factors in here will lead us to CO AirFree. So if we can get our hands around this excess air factor and the carbon monoxide and combine them together, we can get this measurement called CO AirFree. Let's take a look at this in another little way here. So we have the combustion diagram, and on the left-hand side of the axis, we have increasing concentration of the flue gas components. These are where the concentrations are increasing or going up. Let's draw a line here called the stoichiometric line, which would be the line of perfect chemical balance. If, back to that complete combustion diagram we had before, if we just had three things going in and three things coming out, this is where everything would be perfectly balanced, where we have just the right amount of oxygen for the amount of fuel present. And we're doing this in a general sense just to show rising and falling amounts. We're not doing it in an absolute sense here. So on the left-hand side of stoichiometric is incomplete, where we don't have enough oxygen or air, or it's too fuel rich. And on the right-hand side, we have enough, or maybe too much oxygen and air, and perhaps fuel lean. So that's another way of looking at excess fuel to the left of stoichiometric and excess air to the right. And this axis here on the bottom shows the increasing concentration of air going into the combustion system. So we'll draw on this line as we increase the amount of air going into combustion. It actually starts from 0 at the stoichiometric line. And that might be a little irregular, something you might take note of. What's happening here is before this point, there's not enough oxygen to go around, and it's actually being all consumed by the combustion system because there's excess fuel for the oxygen available. And it only starts appearing, the oxygen signal, the excess oxygen in your flue gas sample that you're getting, that you're extracting with your combustion analyzer, is only available, only seen on the meter past the stoichiometric line. Now we'll just throw in the line of carbon dioxide concentration. So on the left-hand side in incomplete combustion, as we have more and more oxygen available, we get to a peak point where we're producing the maximum amount of carbon dioxide. And that's because it's actually the byproduct of all the carbon in the fuel and sufficient amounts of oxygen. You get to the peak in carbon dioxide. Beyond this point, actually, the carbon dioxide drops off. It's not because any less is being made, it's because these are all volumetric concentrations. So it's how much out of the whole is present. So if we're adding in extra amounts of air, then we're actually diluting the amount of carbon dioxide in the system. So that dilution factor is part of what we're trying to get away from when we look at CO AirFree. This black line that was just thrown in here is actually the line of carbon monoxide concentration, showing that it is actually decreasing in concentration. The amount of carbon monoxide produced decreases as you move from insufficient amounts of air to sufficient amounts of air. So as you have more and more air available for combustion, more and more of it can be converted to CO2. So as the CO2 rises, the CO drops. And we show this crossing into past the stoichiometric line just to show, like in the real world, there is some CO present even when you do have excess air present in systems, just because combustion is such a chaotic process and things are not happening consistently and perfectly at all times. Here's a line of combustion efficiency just to show you that the combustion efficiency is also one of those parameters that peaks out about in the same place, the same time as carbon dioxide peaks out. So in a system where you create the highest amounts of carbon dioxide is a system where you're creating the most amount of combustion efficiency. If you have a question here, is the percent of incomplete combustion the inverse of the efficiency of the unit? Well, basically, the stack loss is what's calculated by the combustion analyzer, and 1 minus the stack loss is equal to the efficiency. So if there's 12% energy loss up the flue, 1 minus 12 would be 88% combustion efficiency. And this isn't a session really in combustion efficiency. You probably want to attend another webinar to understand more about that, because we do go into the differences between AFUE and other factors and combustion efficiency. And they're not exactly the same parameter, although they do point in the same direction. And here's just, we've added in the line for smoke, just to let you know in oil, to cater to the oil burner market, to show that that is a decreasing parameter. There's less raw carbon particles being produced, and that's what smoke is as you go towards the stoichiometric line. And here's the ideal range for the operating for most burners, where you have no smoke, very little CO, some amount of oxygen, excess oxygen, not your peak, but close to your peak CO2, and the peak amount of efficiency coming out of the system. Let's take another look at this, specifically with regard to the CO AirFree situation. So we'll put that oxygen line back in there. This will be a little bit simpler version of the graph, and the CO line in there. Now, if we could somehow use a calculation between CO and oxygen to find out what this crossover point is here, where it crosses through the stoichiometric line, where it breaks through the stoichiometric wall, that would be your CO AirFree reading. And that CO AirFree reading would basically not change value as you moved across with increasing air going to combustion. So this is a CO reading that's less sensitive to the excess air concentration. So here, we'll take a step back and see as oxygen increases, CO can drop pretty dramatically. So we're sort of spoiling the CO signal, the CO availability of that measurement as it crossed over the stoichiometric line, because we're diluting it with oxygen. Now, if we can remove that dilution factor or look at CO AirFree, we would have pretty much one consistent number moving across here. So I believe this is one of the reasons why BPI chose or looked at this, the CO AirFree. It is a way of that the appliance manufacturers are measuring their equipment. This is a field method for being able to calculate the air-free concentration of CO. So it basically backs you up to that point where it crosses the stoichiometric line. Now let's dig in a little bit deeper and take a look at the concept of undiluting. Now, how can you undilute something? Let's do a little thought exercise here. If you took 1 tablespoon of sugar and placed it into a glass of iced tea, that glass would have a certain sweetness level. For some people, it might not be sweet enough, but you could certainly detect that level of sugar in the glass of iced tea. If you put that same tablespoon of sugar into a pitcher of iced tea, for some people you might not even notice the sweetness, the increase in concentration, because there's so much excess iced tea diluting that concentration of sugar. So which one is sweeter? The apparent one that would be sweeter is the glass of iced tea that has much less dilution present in it. The one that has more dilution, or the pitcher of iced tea, would be much less sweet. Even though it has the same absolute amount of sugar in both, one would taste different than the other. So if you're using an analyzer which measures relative concentration as to how much sweetness or how much of one thing is present based upon the whole, like a carbon monoxide meter, just a straight carbon monoxide sensor looks at the percent of carbon monoxide compared to the whole. Even though it's the same amount of sugar in both of these, this would appear sweeter or have a higher concentration of sugar than this would. So you can see the effect of diluting your signal or diluting out the thing that you're trying to measure, the sweetness or the carbon monoxide. They both have the same amount of sugar. Neither has more sugar, but it's hard to detect that sweetness difference. I was just checking a question here. If we're able to evaporate all the water or the tea that's in both of those vessels, in those pitchers, we would end up basically with about the same amount of sugar in both of them. We'd end up about a tablespoon of sugar in both. So even though it was the same amount, the same concentration, the same raw amount of detectable thing present, the sugar, we were unable to measure it without looking at a way of undiluting it, of evaporating it and removing it. So the CO AirFree calculation actually does this within the combustion analyzer. So it takes the raw carbon monoxide reading, which comes from the sensor, which is a volume concentration, or consider it the sweetness or the amount of CO concentrated in the total flue gas sample, and then takes the factor of oxygen, or that diluting element, or this is the excess air, the excess water. This is how we get a grapple or a handle on how much excess air there is, by looking at the oxygen level. So the two sensors that are required in your analyzer to do a CO AirFree calculation are the CO sensor and the oxygen sensor. So this raw value is the as measured value. It'd be just that ppm value, but that ppm value can be affected by how much diluting air is present. One thing to keep in mind if you're to work through this, and we will in a second, we're actually going to go through a spreadsheet that I'm working on that I will be able to share with people, so you can actually see this calculation sort of happen before your eyes and dynamically. Most analyzers do stop the calculation when it gets over to 16 to 18% oxygen. That means it's very close to ambient air conditions, recalling that ambient air is 20.9% oxygen. So when you get up to that point, the CO AirFree calculation, the CO AirFree number is usually pretty large, and it's a little bit hard to get a grapple on. So it's usually not a combustion situation. So we're looking at levels for most analyzers below 16% oxygen is where the CO AirFree calculation does actually get performed. So let's jump out here and take a look at a spreadsheet. And this is the spreadsheet I mentioned that will be available shortly. So this is a CO AirFree calculator. It's a lockdown spreadsheet, but there's a few boxes in which you can type some data and see what's going on. So if we took in this first box here, this is a dynamic table that would show you if you had a raw CO reading, the CO reading from your CO sensor, and then various oxygen levels, what it would do to the CO AirFree calculation. So let's put in, for example, 50 parts per million. And of course, at 0% oxygen, it is air-free. There's no excess air present. So it would read 50 parts per million. But as you move up into increasing levels of oxygen, let's say 5% oxygen, the CO AirFree reading is really 66. As you move to 10% oxygen, the CO AirFree reading is 96. As you move to 15% oxygen, it gets up to 177. So it's over 3 times higher based upon the amount of dilution here. Let's put in 100. And you'll see that that factor pretty much holds through. That's why we have this CO AirFree factor here, just to give you an idea of how much oxygen is present. That's how it's going to affect or actually increase the CO AirFree reading. So remember what CO AirFree is we're undiluting the concentration. We're removing the effect of excess air or excess oxygen on the system. So as you put in different values here, 200, you'll see that it increases the value as you go up, still about by the same factor. So this is just gives you a little idea here of how at various oxygen readings, the same CO reading would have a different CO output. Let's take a look at another one here. You can actually put in two readings and get the reading out here. So we'll put in 100 and 6% oxygen. So we'll do the same over here just to show the two work. We have 100 parts per million, and at 6% oxygen, 140 parts per million CO air-free. Same thing here. At 100 parts per million, the oxygen reading at 6%, you would get 140 CO air-free. So this is just a couple different ways of looking at it based upon a chart with different oxygen readings, or just a dynamic calculation where you have to enter in two different values in order to get your CO air-free calculation. Here's another table that's created that covers a level of CO, the combination of CO and oxygen that combine to be close to 400 parts per million CO air-free. That is one of the standards for the unvented appliances that they're looking for from a manufacturer standpoint. So this is this will give you an idea of what combination between CO and oxygen reading would lead you to a CO air-free reading of around 400 parts per million. So you can see there's different ways of getting to the same level. But so even at 150 parts per million, 13% oxygen would lead you to 397 parts per million of CO air-free. So I hope this gives you an idea of how all these things kind of work together. It's a combination of CO reading and oxygen reading. And if you have pretty much any combustion analyzer that I know of that has a CO and an oxygen sensor in it, you are going to get this CO air-free or CO undiluted calculation automatically. You don't need to use a spreadsheet like this. However, if you do have a meter that reads CO only, you're going to be at a disadvantage. You're going to need either to get or acquire an oxygen meter by itself and then do this kind of calculation of this chart, or to look at replacing your CO only meter with a CO and oxygen meter, which is basically a combustion analyzer. Okay, so let's go back to our presentation here. So let's take a look at the math here, and let's just do one calculation. So on this screen, you can see in this particular combustion analyzer, you can see 11.2% oxygen, and CO is 22. And we'll go ahead and jump out back here again, 11.2 and 22. So let's put in 11.2% oxygen and 22 parts per million CO. We get 47 ppm CO air free. That would be indicated. And drum roll, please. Hopefully things work out. Yes, so we do get 47 ppm. And in this case, this testometer, the 330, it's called CO undiluted, UNDIL. Perhaps if there's a firmware change, it may say CO air free on it, but just so you know, CO undiluted, COU, CO undilute, these are all readings for the same thing. Okay, back again here. So BPI 1200, section 7.8.5, does have a reference to the ANSI standard, which is also joint BSR standard, Z223.1, and it's also part of the NFPA National Fuel Gas Code, NFPA 54, where it talks about CO thresholds from different types of appliances. And this is basically what they're trying to align with. That's what a national standard does, is it aligns with other standards. It doesn't create all the good work that's been done out there, but it amplifies or builds upon that. So for central furnaces, all categories, 400 ppm CO air free is the threshold limit, which they're looking to have no more than. Vented room heaters, 200 parts per million. refrigerator. If it was a combustion combustion type refrigerator, 25 parts per million. Gas loft, etc., gas dryer, that kind of thing, 25 parts per million from a top burner on an oven or cooktop. So here's basically what's part of the standard. Here's the action levels, what you're governing for. You're looking to have appliances test out below that threshold limit. One important comment here is this particular table, G.6, is subject to a public ballot, a ballot and public review for its before, and it may be revised before that point. So this is provided with the permission of AGA, American Gas Association, for people to overview. And again, we talked about before about being kind of in a weird stage where things are in transition, but I think that's a good thing for the industry. There's a lot of transitions going on, and you just have to kind of keep on your toes and stay on top of things, attend webinars, do reading, check with colleagues, check with experts, check with who trained you to make sure, and the manufacturers to make sure you stay up on things. One thing notably missing from here is what about oil systems? And I have put the call out to the oil heating community and asked them what levels, because this has got to do, this table here is specifically to do with gas burning appliances. I don't currently have my hands on, if anyone does have their hands on anything for oil heating, that would be great to get a hold of that, and we could incorporate it. So the CO AirFree, there's actually a lab test procedure, and I'm going to go over the lab test procedure. It comes straight out of the standard from the ANSI Z21.1 1993 edition, and go over how it works for a cooktop, for a gas cooktop. Just to give you an idea, this is a third party, usually third party or factory test that's done to make sure that the products, the combustion fuel burning appliances, meet or exceed the, or better than the standards. So this is not the kind of thing you can do in the field. That's why you need to have the CO AirFree calculation to do some kind of field fix on what that is. So in this case, pans containing 5 pounds of water each are placed on top of the 4 range top burners. And all range top burners in the oven are operated simultaneously. Again, this is directly from the standard. And after 5 minutes, the AirFree CO is measured in a collection hood above the range. Now, this isn't something you could easily do in the field, but this collection hood basically is dropped over the range and adjusted until there is no longer an oxygen concentration inside the hood, and that means there's CO AirFree. There's just enough oxygen going in to feed underneath the hood, but there's no excess air going in. So they basically throttle the amount of oxygen going in until it gets to this air-free situation, and then that measurement is what's made for CO AirFree. The one that we use in the field in the combustion analyzers is different, of course, but it's a little bit easier to achieve in the field. So basically looking for no more oxygen going into the system. There's just enough oxygen to take you to that point of stoichiometric we talked about before, backing it up to the stoichiometric wall, and then seeing what that carbon monoxide reading is. There are a lot of good papers and resources out there if you want to delve into this a little bit more. And I do see some questions have come in, and I will go ahead and answer those after we get done here in the next couple minutes. But Rick Karg has done a tremendous amount of work in this area. This is actually from his from karg.com/papers.htm. You can go to his website and see the different work he's done in terms of air-free measurement. And this is his. Basically, he's done a lot of good work here. These clickable links are things that you can go to his site and actually download his papers on carbon monoxide, and especially on carbon monoxide air-free. A lot of credit to Rick Karg here. So let's back it up to the point where we know where the standard applies, we know where it's coming from, we know where we're asked to be doing it, we know it's required in the tools. So what are you looking for in a measurement tool in order to be able to do the CO AirFree measurement? Of course, we're going back to the 0 to 2,000 parts per million as instructed by BPI 1200, doing the CO AirFree measurements built into it. So that means it must have a CO and an oxygen sensor present, and it must also be able to do that calculation. that we're looking for 1 parts per million and about 5% accuracy on the CO measurement itself. And there's one factor here which I'm promoting to BPI to take a real close look at, but not currently in the standard, is to use a NOx filter for the CO sensor. If you've attended some of my previous combustion webinars, either seen me out there in the wild or seen the webinars online or attended them, you'll know I'm very passionate about this having NOx filter for the correct CO measurement. Let me tell you why that's important right here. Oxides of nitrogen are present in almost every combustion system you're going to encounter. They come from mainly the nitrogen in the air. There are other sources, but mainly the nitrogen in the air and the oxygen in the air. And it's an oxidation of that nitrogen that happens, and it causes it to create a number of different species: nitric oxide, nitrogen dioxide, dinitrogen pentoxide. Mainly the one we're concerned about here is NO. We often call it NOx, but it's the primary element in a flue gas. Is about 90 to 95% NOx. Of NOx is NO gas. NO does, as it moves out of the combustion system, it does convert, and it's a time frame about 35 to 40 minutes. It does convert to NO2, so it does kind of fade away, so to speak. But inside the flue, while the combustion system is operating, there can be large amounts of NOx present, of nitric oxide present, in concentrations of 40, 50, 100, 150 or more parts per million. The reason why we bring it up, nitric oxide tricks or fools a CO sensor. It fools a CO sensor into thinking that it is actually reading CO when it's actually reading NOx. It's reading nitric oxide. And it's a factor of about 40 to 50%. So for example, if you have 100 parts per million nitric oxide, you would have, it could show up on an unfiltered or unguarded CO sensor is 40 to 50 ppm of false CO. So you're really not reading CO at this point, you're reading nitric oxide. If you're trying to make a decision or determination based upon CO concentration and you're also measuring NOx, you've kind of messed up your measurement. There's also some other factors like hydrogen you might hear about that fools a CO sensor, but hydrogen is only produced at extremely low excess air values. It does also mess up the reading on a CO sensor, but it's got to be at extremely low excess air values that it would happen, and that's not something that you would encounter typically in a combustion system you're going to be testing. So our recommendation here from TruTech is that you never measure without a NOx filter. It comes standard in all testo equipment. It's included or available for backrack or other models of products. It can be an internal or an external filter. Picture up here is an internal NOx cartridge filter in a Testo 327. And below this is a correct measurements. This is the brand we sell. It's $39.95, I believe, and that includes shipping for just this NOx filter that lasts for a good period of time, lasts for exposure. It's kind of like a sponge. It soaks up as much NOx as it can, but it gives you a nice clean CO reading, which is really what you're looking for. If you're going to be making determinations and making judgment calls on CO AirFree, you really got to make sure you have a good CO reading to begin with. And this is to show a situation where we have 6 parts per million on the left-hand analyzer and 27 parts per million on the right-hand one. These two probes are side by side in the same combustion flue, measuring the same gas concentration, yet you see a difference of about 21 parts per million. You also notice here that you have 38 parts per million nitric oxide. That's the element that we talked about that messes up or tricks or fools a CO sensor. And if you take about 50% of that, you get about 19. You add 19 and 6, and excuse me, you have around 25 to 27 parts per million. So basically, this nitric oxide is messing up the reading and showing an excessive amount of CO, which was then show an excessive amount of CO AirFree, which could put you in a situation where you're making a judgment call based upon a CO AirFree fail. But if you're not doing it with a good CO reading to begin with, it kind of compounds the situation. So if you want more information on this, we do have a white paper that I helped work on when I was at Testo at bit.ly/NOxTruth, all uppercase, and you'll be able to download a paper. It talks a little bit more about the comparison here. I'm not doing any brand bashing here, but just pointing out a technical fact. There is a difference if you do not measure with a NOx filter. you will get a difference in CO reading. That CO reading could cause you to make an incorrect judgment call. Okay, I do have a few questions that backed up. I'm going to try to answer these right now. Working backwards. Yeah, the new threshold limits were in this presentation. I will send a copy of the presentation to everyone who registered for this, as well as a link to the YouTube video. Just make a note of that here. Copies of the spreadsheets, as soon as we've done our QA on them, we'll make sure they get out to you. Why do manufacturers aim at 400 parts per million CO AirFree? Marilyn, I think that comes from some testing that was done. There may be some debate over that. I've heard some things like it was done with different housing construction standards from the past. I'm not exactly sure on where that comes from, the 400 ppm CO AirFree. I'll try to research that and be better prepared for another session here. For determining CO levels, aren't raw CO and CO AirFree going to result in two different interpretations? Absolutely. Well, basically, your raw CO reading is what's in your ambient concentration, and CO AirFree is your appliance concentration. So this is, I'm going to go ahead and pause the screen because I'm showing everybody's names here. That's really not correct. So what we're trying to do here is the raw CO is a reading that would be usually in the ambient situation, and that's the breathing air that's subject to dilution. CO AirFree is that what's in the stack or near the appliance, and that's basically going to be an evaluation of the appliance. So there's two different things going on here. One is the CO that could affect someone directly from a health, safety standpoint, and then there's also the CO emitting device, and is it out of specification? So yes, there are two different interpretations for this. One is for health and safety, and one is for appliance compliance. Yes, someone is going back to the analogy. CO is the sugar, and O2 is the iced tea, or the dilutant, the thing that's diluting the sugar. So that is correct. And someone corrected me that CO is a triple bond, and I will double check that through another source and then update my slide. Thank you, Brian. And we do have one final question here. The only problem that I know it's relatives is it tricks a CO sensor, otherwise it's harmless. Actually, nitrogen dioxide, NO2, is a toxic gas. It can form nitric oxide in your, or nitric acid in your lungs. So levels of that, you do want to minimize exposure to levels of that. But usually, again, that's a very low amount coming out of a combustion system, and hopefully the combustion system is properly vented and it isn't getting into a living space. But nitric oxide is not a safe gas, or NOx is not a safe gas. It's also a precursor to ambient air pollution, to smog, that kind of thing. Okay, so we'll just cover here and resume broadcasting. Just a couple of different links here for you to get in touch with and keep in touch with True Tech Tools. Best place is probably our newsletter. When you put in our newsletter mailing list, we'll keep you up to date on webinars, sales, specials, technical discussions, downloads, guides, that kind of thing. Our event calendar is where you'll find out about the webinars, where we're doing presentations, where we're doing out there at trade shows, etc., and see Facebook page, blog, etc., different places you can be in touch with us. Yep, I think that covers it. So I'm going to stop the recording here.